Howdy, my name is Jian. I'm a assistant professor here in the School of Performance, Visualization, and Fine Arts. And I'm also assistant director for project development at Texas A&M Institute of Data Science. And starting last October, we built this Texas A&M Digital Twin Lab. And we are trying to develop the key research capacities on digital twin development. And we are focusing on the simulations and visual modeling and networking and all the components about digital twins. So today we are delighted to invite Youngsoo Choi here to give us a talk about the physics-guided data-driven simulations. So Youngsoo, as you all know, is a computational math scientist from Lawrence Liverpool National Lab. And his research focuses on developing efficiently reduced order models for various physical simulations. And his expertise includes various scientific computing disciplines. And he's currently leading the effort to develop LeapROM, and also Landcourse ROM. He earned his undergraduate degree in civil and environmental engineering from Cornell University, and his PhD degree in computational and mathematical engineering from Stanford University. And he was a postdoc scholar at the SINDy National Laboratories, and also, SINDy National Laboratories and Stanford University prior to LLNL in 2017. So with that, I'll hand over the microphone to you, Youngsoo, and I hope everyone will enjoy his talk just like what I did with all his presentations on YouTube, which is very, very rewarding and informative. Thank you so much.
Thank you. Thank you so much for the wonderful introductions. I don't know. I deserve those nice introductions. Well, thank you for the invitation. By the way, let me check. Am I sharing the full screen or the
yes, it's a full screen.
Okay, great. Just wanted to make sure. All right. I'm glad to be here. Very honored. Thank you so much for the introduction again. As the Jian introduced, my name is Youngsoo, and today I'm going to talk about the physics-guided data-driven simulations. Exciting topic, so hopefully you're gonna enjoy this. So before I dive into the real meat, I would like to introduce our reduced model teams and also wonderful internal and external collaborators. Without them, I wouldn't be able to present what I'm going to present today. So big thanks to them. All right. So physical simulations play an important role in modern science. It can not only, provide nice figures like and movies, which I have shown here, but also very detailed information which you wouldn't get from observed data or the measurement data from the experiment. So that's why this concept of the digital twins, arise because of this capability of the physical simulations. But the only problem they have, the potential problem they have, is even with the world-class high-performance computing machines, for example, at our lab, Lawrence Liverpool National Lab, El Capitan, these simulations still takes on hours and days or sometimes a week, which is really problematic, especially for the multi-query applications such as design optimization, inverse problems, and optimal control problem, and uncertainty quantification, right, where you need to simulate these many times with the different configurations of the parameters and boundary conditions, initial conditions, and so on, right? So we definitely need to accurately accelerate these physical simulations. How do we do that? Thanks to the advance in machine learning these days, we can accelerate these using data. There are many different ways of using data, but one particular way is you generate tons of simulation data. For example, for the Richtmyer Meshkov instability problems, you generate the many different parameterized initial conditions, and you let your high fidelity full model solver and generate the time dependent the field, the evolutions as an output, and you generate these many input and output data. And using those data, you can fit those into some sort of neural network, whatever that is. For example, here we fit our data into the 2D convolutional neural network with the tunable parameter of 78 million. And sounds daunting, but there are many the powerful tools available, and with HPC, especially with the GPU, you can tune those 78 million parameters to fit those data into this neural network. And once it is done, then you can predict new dynamical solution for this Richtmyer Meshkov instability problem for the new parameterized initial conditions you haven't seen in the testing phase. And the evaluation of those neural network is very fast. And as a matter of fact, this particular problem, so we get a speed up of 100,000 when compared with the corresponding high fidelity solver. And another nice thing about this approach is you only need data, meaning that it is non-intrusive. You can wrap this framework outside of the physical solver. You have the person who developed this data-driven approach doesn't need to know anything about the how the source code, the physics solver works, and how it is implemented, and so on. You don't have to know anything about it. You just need to get a data from the physical simulation experts. Because of that, it takes very less development time than other data-driven methods, which I'm going to advocate for some reasons later. I'm going to tell you why. And lastly, there are great tools available, such as PyTorch and TensorFlow, and these days JAX is becoming really popular. But in spite of all these advantages of this data-driven approach, so-called the black box approach, it comes with several limitations. First one is being not structure preserving. What I mean by that, a lot of this black box approach prediction, the solutions, they tend to violate the underlying the physical properties, such as conservation of laws, or if there is a symmetry you have to preserve, it tends to give you the non-symmetric solutions. Although in the training you have minimized the difference between the true data with a prediction data, that is not enough to get the structure preserving solutions. So to compensate that shortcomings, of course, they require big data because that's the only thing they rely on, right? So they have to, generate many data and rely on those big data to improve the accuracy. However, in terms of physical simulations we are dealing with, as I said in the beginning of the talk, those physical simulations can be very expensive, right? So generating those data itself is challenging. Also, if the parameter space dimension is increasing, then number of the sample points, number of data you have to generate is even larger, and it's actually increasing exponentially due to the curse of dimensionality. So it's a big problem. And this type of black box approach tends to be not robust for extrapolation. For example, Richtmyer Meshkov instability problem I have shown in previous slides, there's a training regions, and if you go a little bit outside of the training regions and you show the density field at some time, like the last time steps, which I'm showing here in this figure, as you can see clearly, the conservation of mass is violated. All those density field is kind of diminishing, which shouldn't happen. But that's what the ML model is giving us as a solution, slightly right outside of the training regions. So it's not robust for extrapolations, and it's not easily interpretable. black box neural network, what is it? It's a combination of the hidden neurons and a lot of hyperparameter tuning needs to be done. Different activation function needs to be tried, and different number of hidden nodes and the connectivity. You use the sparsity or dense the connectivity. Those are the really the design choice, and it becomes almost like an art. And when finally we get the successful model, after all, why it works, and it's hard to interpret why it works. And when it fails, it's hard to interpret why it fails. That causes us to stumble on the hyperparameter tuning, etc. So we need an interpretable and physics-guided data-driven approach to resolve these issues. And our group, the reduced model team at Lawrence Livermore National Lab, has basically 3 goals to address those issues caused by the black box approach. The one being is the physics guided. We try to incorporate the physics into the data-driven model as much as possible in order to get a prediction from data-driven methods, the structure as structure preserving as possible. And we want our data-driven model to be interpretable. What interpretable model is available out there? Differential equations, right? Since Isaac-Newton era, this differential equations has been invented and developed, and many famous mathematicians has studied on that, and we know what it is and how to interpret these differential equations very well. And if those differential equations somehow is not available in the data-driven approach, then we try to identify those differential equations, governing equations, using the many different physics discovery, the algorithm. So I'm going to talk about all that today, but just to give you some framework, which I'm going to use over and over in this talk, let me introduce those framework. So let's say you have a high fidelity simulation data. I'm not sure why it is not moving. It's supposed to move. Hopefully it's gonna move. Okay, great. Dynamical time-dependent data, 2-dimensional, and obviously it involves many pixels, so it's a high-dimensional data. So because it's hard to deal with the high-dimensional data directly with the data-driven methods, we usually compress those data into small latent space using various compression techniques. For example, linear compression techniques such as singular value decompositions, or nonlinear compression techniques such as autoencoder can be used to reduce those high dimensionality to reduced space. And once those high dimensional data project onto the reduced space, then you end up with the trajectory, the lines with a few degrees of freedom, because we have reduced that to reduced space, which is really nice to fit those data into some sort of model, right? So in this phase, we identify some underlying physics governing equations, which describes the reduced order, reduced space dynamics, as you can see from here. And once you identify those governing equations, it's easy to solve that governing equations because it's within a very small reduced space, and you solve that. And then you reconstruct the full states by some mechanisms, such as the decoder, or if you use the linear compression, then using the reduced basis, you can reconstruct the full states. And you recover predict the new, the high dimensional, predictions, right? So this is the framework we are going to use to accomplish this physics guided and interpretable and physics discovery algorithm will be useful. All right, so let's ask these questions. How can we identify interpretable governing equations for latent space dynamics? So to illustrate that, let's go back to the latent space dynamics data figure, which I have shown you in previous slide with a dimension of 3. And since it's very reduced and small data, as I said before, it can be easily fit to some sort of model. There are infinitely different possible models you can fit this reduced space data into, but what is the simplest one? Since it is the time-dependent data, ordinary differential equation is that's very natural choice. And among the ordinary differential equations, what is the simplest one? Yes, and the ODE, the linear ordinary differential equation. And if you fit your the reduced space data into the linear ordinary differential equations, it happens to be a very famous the method called the dynamic mode decomposition, which was first introduced by the Peter Schmidt in 2008, just to extract the important dynamic features from the flow data. But later on, the researchers, also identified this dynamic mode decomposition can be used as a surrogate model or the reducible model, and it can be generalized to parameterization case, and it works beautiful. So if you use this method, you can actually accelerate your expensive computationally expensive physical simulations. And nice thing about this is still this is non-intrusive in a sense that it does not require any the knowledge about the physics solver or the numerical schemes it is used in the high fidelity models and so on. You only need the data, and because after you compress those data, you feed those data into this fixed form of linear ODE, right? So let's demonstrate how this DMD performs. And the examples I have picked, I mean, we have many different examples. We have applied the DMD too, but I think this example is pretty cool. So-called the Pore collapse hotspot generations. So just to briefly explain what that is, you have some sort of microstructure with an energetic binder and many voids and the pore regions in random the distributions, and you apply some sort of shock pressure on the left. Then the shock is going to propagate from the left to the right, and as the shock is hitting the pore, and when it interacts with the pore collapses and it reduces the size of it. And as it does, it's going to generate the hot spot, like the hot temperature regions. And those hot spot mechanism is really important to understand because this the phenomena can be applied to many different important applications. So we concentrated and focuses on this single pore collapse phenomenon and try to understand using the image data. And we generated 128 by 128 pixel image data using I don't know, someone can mute.
I just muted them, sorry.
All right. So we have generated 128 by 128 pixel data, and then 180 images for the time dependent the steps. And then we intentionally chose the 5 parameters. So we vary the pressure, the shock pressure on the left from 11 gigapascal to 15 gigapascal. And we did that just to show, how robust the DMD, the performance does on this scarce data. And then later on, we compare the performance with the, some traditional, the neural net approach, the black box approach. So we'll see. Okay, we have applied the DMD, and the slide demonstrates that, the local DMD we built. So the different colors of line, the blue, red, yellow, and purple and green. These are all different the local DMD. So for example, yellow is built using those image simulation data for the shock pressure of the 13 gigapascal, and using those local DMD models, what we did is we predict the solution for the pressure, the Pore collapse, the phenomena for the 11, 12, and 14 and 15. Obviously, this is the extrapolation case, and even though it is extrapolation, DMD was doing pretty well. As you can see, this one is for the yellow, the DMD is a reproductive case, and the 14 gigapascal is the predictive case. 14 gigapascal, it gives you the maximum relative error of around like the 5%. And as you can see in eyeball norm, both DMD and the true solutions, they are almost identical. The third one is showing the error, the difference between those two. All right. Of course, if you include more data and use that to build the parametric DMD, then the accuracy level obviously improves. The local DMD, which only use the 13 gigapascal pressure case, and if we add 11 gigapascal case and 15 gigapascal case, and obviously the accuracy of the DMD improves. And we have compared the DMD to the black box approach, so-called the continuous, the conditional generative adversarial neural network. And yeah, as you can see, the DMD outperforms the CC-GAN. It is because we intentionally use the scarce data, right? I mean, normally the neural net model, you need a big data, as I described in the beginning of the presentations. With the scarce data, it is hard for them to achieve a good accuracy. But the DMD model for this particular problems, it was able to outperforms the CC-GAN. This one is showing the extrapolation. So overall, the accuracy level of the DMD was at the worst 12% relative error, while the CC-GAN was around like close to the 50% relative error, which is showing DMD is really outperforms the CC-GAN. Not just for the extrapolation, the interpolations, the CC-GAN improved, by adding more data, but still, the maximum error is around 25%, while the DMD is like 5% at maximum relative error. So DMD, if you use it properly, and really it can be really powerful. And the training itself of the DMD is only requires the speed types of the compression. So the training cost of the DMD is a lot less than the CC-GAN. So yeah, so take advantage of it. All right, let's go back to the steps where we identify the latent space dynamics again. Here, instead of the fixed form, we can actually provide, use some sort of regression techniques, such as the SINDy, which stands for the Sparse identification of nonlinear dynamical systems, which was invented and popularized by the Brunton and Proctor and Nathan Kutz group. So if you have the trajectory data, and what the SINDy does is you can fit those data into some model, just like the fixed form model. But instead of you fixed the form, well, initially you fix the form, the user provide a library of the right-hand side, the functions you can use in the ODE to describe these dynamical systems. But once you provide those library of the functions to be used in the right-hand side of the ODE, it enforces the sparsity and try to come up with a parsimonious ODE model by the zeroing out the coefficient of this provided user functions, so that it comes up with a as simple as possible the ODE, the form to describe this dynamical systems in latent space dynamics. So yeah, definitely you can use the SINDy to identify those. And as a user, you can provide any types of the functions, and this SINDy sparse regression technique is going to give you the the parsimonious the ODE, the differential forms. So that's obvious choice, and we actually did that. And just to talk about how we parameterize this framework, let me explain how we do the parameterizations. To explain that, let's say we have a two-dimensional parameter space, which is defined as D. And we have, as any data-driven approach, you have to sample those parameter space. Let's say you have sampled a mu1, and let's say you built the latent space dynamics identification model with the SINDy, and let's say the SINDy identifies this specific coefficient a hat of mu1. And then you do the same thing for the parameter mu2, mu3, mu4, mu5, right? And then for the predictions, you got mu star, which is the point you never seen in the training data. And you somehow have to use the existing LASTI latent space dynamics identification model to come up with a new the LASTI model for the mu star, right? And obvious choice is to use the existing coefficients, a hat mu1, a hat mu2, etc., up to a hat mu5, and interpolate those coefficient the matrix to come up with interpolated the coefficient matrix a hat mu star, for the new parameter value mu star, and that's how you get the interpolated the LASTI model, and you solve it, and the reconstructed to the full states, and yeah, you get the predicted, the parameterized the solutions. As you can easily see, this framework can be applied to not only this particular point mu star, but many other points you haven't seen in the training data, and apply that to parameterize your the LASTI model. So we have try that, and just to show you how it performs, this is the rising bubble, the examples, where we introduced the two different parameters. The rising bubble, it's pretty interesting application as well. A lot of engineering applications, the heat transfer through the bubble is kind of the key mechanisms which is widely used in the heat transfer and also the refrigeration and so on. So it is really important to understand this kind of mechanism. And we have applied the LASTI method, the latent space dynamics identification method, to this rising bubble case by changing the two different parameters. The bubble size, which is characterized by the radius of the initial bubble, and also the maximum, the initial temperature of the bubble. And we vary those two parameters and generated the 3,000 images per each the points of this parameter instances, and we used the 100 by 100 pixel resolutions. And using those data, we built the LASTI with a latent space dimension of 5, and providing the linear model as the SINDy. And we use the SINDy to identify the latent space dynamics, and the LASTI model, we built this rising bubble, works pretty well. And this graph is showing how does those latent space dynamics 5 degrees of freedom changes with respect to time. And this one is the true dynamics of the rising bubble, and this one is one of the predictions by the LASTI. And the standard deviation is computed, absolute error and absolute error is also computed. And as you can see, looks pretty good. And let's, visit, the sampling, the procedure. As I said before, the data-driven approach needs to go through the sampling procedure, right? You have to pick the training data from your parameter space, and there's choices you can make, right? You can either use the uniform sampling or Latin hypercube sampling, such as like space filling, sampling methods. You can do that, or you can use some sort of active learning approach, where you try to be smart about where to sample by taking the iterative method. So we did 2 different samplings and compare the performance. And for the rising bubble problems, if you use the uniform sampling, generating 25 data points in training data, then the maximum relative error becomes 8.3%, the last model achieved. While if you use the greedy sampling, even though we have used the same number of training data, the maximum relative error decreases to 6.2, like the 2% the improvements, just by simply using the greedy sampling over the predefined, the space filling, the sampling. So how does it work? The greedy sampling starts with some, the predefined sampling points. Let's say for corner points, we have generated the data by simulating the corresponding high fidelity simulations. And then you train the last model, right? And in the last model, you have to introduce the reconstruction loss terms and also the 2 different loss terms related to the SINDy, the sparse identification of the nonlinear dynamics. You go through several epochs, and until you are sure that your last model is mature enough, then you go back to this sampling procedure. When you go back to the sampling procedure, as I described before, you have to interpolate those last coefficient matrix A hat, right? And there are many different ways of doing the interpolations. And if you particularly choose the Gaussian process as an interpolation technique, then what is nice about the Gaussian process is that it gives you the point of the maximum improvement you can make, and you can explicitly use that quantity information to choose where to sample next, right? So for this particular examples, this point was the point with the maximum improvement. So you choose that, right? And then you choose that, and then you invoke the high fidelity solver and generate this simulation data there, and then include that data into the training, going back to here, and you go through several epochs again to incorporate the new data and improve the autoencoder and SINDy simultaneously, and then you go back to these iterations and you invoke the GP, and you repeat this process until you obtain the overall the last model achieves the desirable target accuracy, right? So as you can see, this active learning framework guarantees to give you the data-driven model, which ensures some desirable accuracy is achieved. So very nice. Going back to this the sampling procedure, in this example, we have used, we have taken advantage of the Gaussian process because it gives us the point with the maximum improvements. But that was statistical information, so not the real physical information. Well, guess what? You can actually introduce the physics informations and let the physics guide the sampling procedure. So, for example, this whatever the last model, which is the generate or trained intermediate of this active learning process, that is going to give you some predicted solution in parameter space, right? And those solutions is high fidelity after the reconstructed to the full states. And since it's high fidelity solutions and a high dimensional solutions, you can plug that back into the original governing equations if that exists, right? For the rising bubble and many other physical simulations we are dealing with, there are known governing equations, right? So you can plug those ML solutions into the governing equations and you can compute the residual out of it. So which does not require the solution of the governing equations. You simply plug that ML solutions and the compute the residual. Many physics solver has a capability of doing so. So you take advantage of it, and among this parameter space, that residual norm is going to tell you where this current ML model is the weakest part by looking for the maximum residual norm, right? So in that way, you can let the physics derive this sampling procedure instead of the statistical measure. So the active learning can be done by physics-informed way. If you do that, and then for these problems, we have applied this lastly to different simulation, the spiral, the advection problem. And this is the comparison between uniform sampling and the physics-informed greedy sampling, which I just described. And if you use the uniform sampling, then you will get a maximum relative error of 5.4 along this line of the parameter space. But if you apply the physics-informed greedy sampling, then your maximum relative error becomes 2%, which is a more than factor of 2 improvement just by incorporating the physics into the greedy sampling. Both of them uses the 25, the training data. So quite nice.
And so there were 2 questions in the chat box. Can you take a look at those 2?
Okay. So Akash asked, what does the color and transparency in the 3rd column on slide 19 correspond to when choosing the 5th point? Oh, okay, so this one. So I think Akasha is asking about this. So this one is either showing the residual norm at this particular points, right? And if you use the physics-informed greedy sampling, we are looking for the maximum residual norm. So we test a bunch of the points in the parameter space in randomly and choose the point with the maximum residual norm. So in this particular demonstrations, this particular point was giving us the maximum residual norm of 9.5, I believe. It's pretty small. Oh yeah, 9.5. But rest of them, the residual norm is pretty good, 0.2, 0.2. So you don't have to sample more on those reasons. You only need to sample the point where the current machine learning model is the weakest, right, to predict the accurate solutions. Okay, and then another question by Srinivas. Could any adaptive sampling technique with respect to the gradient of black box function improve the situations? Yeah, I mean, so I believe so. I just introduced 2 different ways of doing the adaptive sampling, like using the active learning framework. And 2 criteria I have introduced was the statistical measure from the Gaussian process, and if the governing equation is available, then you can actually incorporate the physics into this adaptive sampling. You can try many other approach, and yeah, and for sure, at least those performance is going to be as good as the non-adaptive sampling, such as the uniform sampling or the Latin hypercube sampling. Yeah, so as answer to your question, Srinivas, yeah, I believe so. Yeah, and that's what I have seen so far with these two different types of the active learning framework. Okay, so where I was. Okay, so let's, okay, this is an ongoing project with a collaboration with the Colorado. The folks there in Colorado, they came up with a SINDy. It's a, different takes from the original SINDy. When the original SINDy, was using the strong form of the ordinary differential equation as a model to fit the latent space dynamics into. But a lot of times, if your data is noisy, then it's better to use the weak form instead of the strong form, because the weak form kind of, with the integral forms, you can smooth things out and then filter out the noise automatically. So we have applied this weak SINDy as a identification method of the latent space dynamics and for the noise data. And as we expected, if we use the weak SINDy, and we call it weak LASTy, and if we use that, even though we increase the noise level from 1% to 100%, we still get the relative error of the weak LASTy, maximum, like the 6% or 5%, even better. But original LASTy with the noise data, with the strong form of the ODE as an identification of the latent space dynamics, as you can see, the error is really, really bad. So I hope to make this work available pretty soon in archive at least, so you can take a look at it later. All right, so let's switch the gear to the physics constraint model. I haven't talked about, I have talked about how to incorporate the physics into the sampling method, but not directly into the data-driven model. So far, I was, introducing the methodology where you can, fit those latent space dynamics data into some fixed model or the SINDy types of regression, the ODE models. But I haven't really talked about how to incorporate the physics into the data-driven model. So let's go back to that. In order to demonstrate that, let's look at the latent space dynamics data with a dimension of 3 again after the compressions, right? If there is a governing equation exists, like which is indeed the case for many applications, like the Navier-Stokes, Maxwell equations, transport equations, Boltzmann equations, and so on. There are known governing equations, right? And if those governing equations are available, why not use those original governing equations to derive the governing equations for the latent space dynamics? And is it possible? The answer to that is yes. And if you actually do that, then you are actually using the projection-based reduced low model, which has been around at least 3 decades or 4 decades by now. And a lot of literatures and many awesome works has been available on this projection-based reduced model. But just to demonstrate how it works, let's say you have a governing equations described by this ODE. You can view it as a semi-discretized version of the partial differential equation after the spatial discretization, right? And W is your state variable, T is your time variable, mu is your parameter, okay? Some generic parameter, whatever that is. Okay, and in projection-based reduced model, you first approximate the solution. You come up with some compact representation of the solution. And the requirement of that solution approximation is that number of unknowns has to be a lot smaller than the full order model states W, which typically million or billion. And in the solution approximations, the number of unknown has to be like 10 or 20, very small compared to this big answer best. And how do you do that? You apply the singular value decomposition to the simulation data, the snapshot data, and compress that. If it is compressible linearly, well, then SVD is going to give you the optimal basis, right? And then use that optimal basis to represent the high fidelity solutions in this matrix form. This phi is a tall matrix, so the number of rows represent the number of degrees of freedom in full states. But since that is fixed now, only unknowns you have to look for is W hat, which is actually the coefficient of this individual basis vector. So you form this solution approximations, you take and plug those back into the governing equations wherever the state fields occurs, like W occurs. If you do that, you can easily imagine number of unknowns reduced from high dimensional space to reduced space, but the number of equations is still a million or a billion of them, right? So in order to close the system, reduce the number of equations as well, you apply Galerkin projections onto the equations, and one way of doing the doing the projection is Galerkin projections. You simply multiplying both sides by phi transpose, which is the basis for the solution. And if you do that, you end up with this reduced system of ordinary differential equations. As you have followed these derivations, this ordinary differential equation is actually derived completely from the original governing equation, which we start from, which describes the underlying the physics, whatever that is, right? So this is one way of deriving the latent space dynamics governing equations from the original the governing equations. So obviously you can solve this reduced system of ordinary differential equations by applying your favorite time integrator. And there's one caveat you have to make sure, which is the nonlinear terms. If your original system was nonlinear, then that still scales with the full order model. Every time the arguments of the nonlinear term changes, you have to update that, and you have to multiply by phi transpose. Those matrix vector multiplication is scales with the full order model. So you have to reduce that the complexity of the nonlinearity. And one popular way of doing it is by applying the DEIM, discrete empirical interpolation method, where the idea is really similar to how we did for the solution space. You first come up with the approximate nonlinear terms, like the phi sub f hat, right? And then the key ingredient is that you sample the nonlinear terms. You do not evaluate all of the elements of the F, which is million or billion degrees of freedom. You only sample few of them. That's the key ingredients of this the hyperreduction or discrete empirical interpolation method. That is done by this introduction of the sampling matrix G transpose in front of the nonlinear term F. And then obviously you can solve it if the number of the sampling points is same as the number of bases for the nonlinear terms, then it becomes the interpolations. Otherwise, if you have a more sampling points, then it becomes the least square problems you have to solve. Anyhow, if you solve this and work out for this F hat expressions, you can come up with this ugly looking forms, and you plug these ugly looking forms into this F hat formats and plug these F terms into the original the reduced the ordinary differential equations you have seen in previous slide. Then you end up with this uglier looking the reduced space, the ordinary differential equation after the discretization. But even though it is ugly, many of the terms can be pre-compute. So, and the size of that is really small. And thanks to the sampling matrix Z in front of the nonlinear terms, you do not have to evaluate every single F terms, nonlinear terms. You only need to sample only the elements chosen by the G transpose, right? So that's how you reduce the complexity of the nonlinearity. And then this kind of method has been applied to many different the problems, and by doing so, if you incorporate the physics in this way, it mitigates many pitfalls of the black box approach I have shown in the beginning. For example, the black box approach was not giving you the structure preserving the solutions, but if you incorporate the physics and apply that to seed of blast simulations, where your shock propagation should be really the symmetry, the physics constraint reduced model ensures those symmetry. And also, as you can see, the relative error for the velocity fields, it's way less than 1%. which is guaranteeing you that the conservation of momentum is preserved by looking at it. Of course, we get pretty high speed up, like 22.8% times speed up we achieve. Another the advantage of the incorporating the physics is the superior extrapolation accuracy. So here, as you can see, we built a local physics constraint reduced model for one specific parameter value, which is the initial velocity energy of 0.25. And we apply those local reduced model for extrapolation, go away from this training point. Of course, it deteriorates, but not as much as the black box approach deteriorates. If you look at the accuracy level of the black box approach, then pretty much it blows up right away as you go outside of the training regions. But the physics constraint reduced to the model still maintains the relative error of 1%, even though you go outside pretty far. And another nice thing about this physics constraint data-driven approach is that as you apply this method to the larger scale problem, as you increase the size of the problem, the speed up you get is increasing as well. So that's another way, another advantage of the physics constraint reduced model. And there are many, many different applications. This reduced model has been applied successfully. Lagrangian hydrodynamics is one of them. And then there are many different variants. So far, I have only talked about the way of reducing the spatial degrees of freedom, but also you can reduce the dimensionality of the temporal degrees of freedom as well. And if you apply that to, for example, the transport particle, the Boltzmann equations, we were able to reduce the 10 billion degrees of freedom in space-time to only 10, and still get the relative error of less than 1%, and wall clock the speed up of the 2,700. And there are many other the variants of the physics constraint data-driven approach which can be applied. One is the component-wise reduced model, but just for the time being, let me skip it and then move on to the last topic I would like to share with you. So the solution representations, there can be different possibility. The one I showed you was the linear subspace representation. The problem with this method is that if the dynamics is advection dominated, as you can see from this the movie, the shock is moving from left corner, bottom corner to the rest of the computational domain. If it is advection dominated, because of the Kolmogorov width is decaying really slowly, this linear subspace representation is really not good. And if you use the linear space vector and try to predict the solution of this advection dominated problems, you cannot really. Although you get the pretty good speed up of 26.8, maximum relative error you get is 34.4%. So in order to address this issue, you can replace those linear subspace methods representation with a nonlinear manifold solution representation. And if you do that and follow those projection-based reduced model paradigm, then you will actually get much better accuracy using same number of low rank the dimension, which is 5. And where do you get the nonlinear manifold solution representation? Is we do that using the autoencoder. So if you look at the autoencoder type, there is an encoder and the decoder. If you look at what decoder does, it maps the latent space dimension to the full state dimension. That's what exactly we need for the solution representation for the projection-based reduced model framework. So we use that decoder, the trained decoder, and use that form as a solution representation and plug that back into our equations and follow the projection-based reduced model framework, and you get the really nice the performance. Even use the small number of the dimension. But the thing is that as you can see, we are adding more nonlinearity into the nonlinear problems because a lot of times this decoder they have the nonlinear activation functions. So the hyperreduction becomes really important, and also the structure of the neural network becomes really important. So for example, just to demonstrate that, let's say we have used the two hidden layers in the decoder as a nonlinear manifold representation. In hyperreduction, as I described before, we have to sample, some of the nonlinear terms, right? Let's say only 3 terms are chosen in the hyperreductions to evaluate. But because of the this nonlinear, this neural network structure with the 2 hidden layers, as the connectivity is, shown here, the connected hidden nodes to these chosen nodes number of them is increasing as you increase the number of hidden layers, and actually that becomes the bottleneck of the hyperreductions if you chose to use the deep structure of the neural net. So that's why we intentionally chose the shallow neural network, and also we sparsify those connections between the output nodes and the hidden nodes as much as possible in order to maintain the sparse evaluation capability and without increasing the complexity due to this the neural net structure. So that's what we used, and then that's how we come up with a those performance of the new nonlinear manifold reduced models. So just to summarize my talk, so I have introduced the black box method and interpretable approach, which is still data driven, not much physics is incorporated. Well, I mean, you can incorporate the physics in this approach in the sampling procedure as well if you use the physics informed greedy sampling. But you can also bring the physics into the data-driven model, right? The different categories has the pros and cons, in terms of the accuracy. Obviously, the physics constraint reduced model is most accurate, even with the scarce data sets, right? And in terms of the speed up, the black box approach is very, the non-intrusive way of SINDy key. And because of that, it tends to give you a higher speed up than the physics constraint one. And in terms of the extrapolations, as I have demonstrated in this talk, the physics constraint one is really, really robust in extrapolation compared to the black box approach, where the black box approach is tragically fails. And the last slide before I wrap up the talk, I would like to advertise our software, open source software called the Libram, which is the library for the physics-guided data-driven approach. And we try to be not only useful for internal the users in Lawrence Livermore National Lab, but also the public outside the external users. And in order to accomplish that, we try to make the YouTube tutorials about the reduced models so that the people can get familiar with the concepts of the reduced models, the physics-guided data-driven approach, and so on. And also, we made our the Libram code available public, so it's open source. Anyone can clone it through this GitHub repository, and then if you are willing to, then you can also the contributes, and we can go to the PR process, and then we can merge those contributions to the main branch. And also we have the Libram.net webpage with the many different examples I was not able to show in this presentation, but you could go there and then follow the steps, and you can generate many other numerical examples with the Libram just to get your hands dirty. All right, with that, I think I can finish the talk, and well, thank you for your attention.
Wow, thanks a lot. And so it's really, exciting. All the results are amazing, and it's very informative and useful. So we do have one question in the chat box here before we move to the QA, and you can probably take a look.
I can read. It's from Lucio. Do you believe that variational autoencoders would prove any better since they statistically segregate and sample the latent space based on their mean and standard deviations. Such methods, though, do suffer from statistical issues such as posterior collapse, exposure bias, etc. on fluid physics data. What could be the solution to this, in your opinion? Well, yeah, I mean, as I said, throughout the talk, I recommend you to incorporate the physics information into variational autoencoder model as much as possible. I just, introduced two different ways, right? The one is, bringing those physics information while you are training the variational autoencoder in the sampling procedure, right? And that will, minimize the number of necessary training data and also, overcome these issues you have mentioned here. And also you can, use those variational autoencoder in the nonlinear manifold reduced model sense and, actually bring the physics into the data-driven models. Then that'll be even better. You can take advantage of all those benefits and also the benefits of incorporating the physics into the variational autoencoder model. So that's my opinion and recommendation for you.
All right. Eduardo, go ahead.
Hello, Youngsoo. Thanks for the talk. It was very nice, very nice. I have a couple of questions, if you allow me to ask at least 2 questions.
Yeah, go ahead. Yeah.
Sure. Well, first of all, can you elaborate a little bit more on the differences between the discrete empirical interpolation selection process to your Gaussian process collocation process? I mean, are they related somehow? Because they are.
Well, yeah, it's okay, so it's not related. So discrete empirical interpolation method, it is well, they are related in a sense that both of them are interpolation technique. Right. But this discrete empirical interpolation method is used to, reduce the complexity of the nonlinear terms. So when you apply this physics constraint, data-driven, derive the physics constraint data-driven approach through the projection-based reduced models, you were able to reduce the complexity of the number of degrees of freedom and also the number of equations. But if there is a nonlinear terms, then there is a complexity scales up with the full of the model due to the nonlinear terms. So this DEIM, the discrete empirical the interpolation method, is one of the hyper reduction to reduce the complexity of those nonlinear terms. Right. And we use the interpolation techniques and also the sampling procedure to.
But here you are also selecting points in the domain, right?
The points in not parameter space, but in the nonlinear term nonlinear term space. So if you go back here, this F terms after the spatial discretization, this nonlinear term scales with the full of the model, like the billion degrees of freedom. So we sample those billion degrees of freedom in output of the nonlinear term space. While that Gaussian process I was talking about, it was on the parameter space. So there are parameter space. Okay. Yeah. So because all the data-driven approach needs to sample the training data, and the Gaussian process interpolation was used to reduce the number of those sampling the training data, so that you don't have to run expensive physical simulations as much as. Okay. Yeah. Got it. Yeah.
Thanks. As a second question, what is the have you guys tried anything with porous media? Equations to single phase, two-phase flow, multi-phase flow type of thing in porous media?
Well, actually, yes. I mean, yeah. I mean, with the collaboration with the mean, actually.
I think
we have
was also.
I think it's Siu Chung, right? I think he's
Siu Chung. Well, you mean the Tony Chung? Yeah, Tony is actually Tony is actually from the Texas A&M, and he was the PhD student of the professor Ifende. He's also this digital twins, part of the digital twins lab, or the right?
Yeah,
I don't know.
Yeah, no,
Well,
yeah. Because I mean, I work with him in a little bit on trying to get the reservoir simulation.
Nice.
And trying to do some POD DEIM, discrete empirical interpolation.
Yeah.
And our experience has been mixed. So I just want to get a feeling from you, and because in Pore's media we have all these shock waves, and when you get to two-phase flows, and it seems not to be as robust as you might think. So I just want to get your opinion on that.
Yeah, I mean, as I said before, the shock, the advections and propagations, those are very advective transport-dominated phenomena, and the traditional linear subspace, the linear subspace reduced model, it suffers because there is no way of compressively compactly come up with a compact representation of the transport dominated the problems, right? So in order to overcome that, I mean, there are many different ways of overcoming. If you are really stick to the linear subspace representation, then you can divide the time domain into the several time window. And then we have applied this several time windowing approach to the pseudoblast equation, pseudoblast problems. Actually, the Tony was the co-author of that paper, and one of the paper actually he did the first author on that, and it works pretty well. Although we stick with the linear subspace method, and we can still actually predict the transport dominated problems. But if you don't want to mess up with the time windowing and all those extra tricks, then I really recommend to replace the linear subspace method with a nonlinear manifold, which does not require those additional tricks, but you can compress those transport dominant data using very small dimension in the reduced space. Yeah.
And by the way, thanks for the talk. I'm gonna actually present to your group May 18.
Nice.
Yeah, so I'll be presented to your group. Maybe we can talk by then and go a little bit more insights on using this for reservoir simulation.
Awesome. Yeah. So actually, before my talk, there was Tony was organizing our seminar, DDPS seminar, one hour ago. Were you there?
Yeah. I'll be there on May 18. I'm going to present for you guys, May 18.
All right. Sounds good.
Very good.
Looking forward to it.
That's great. So we do have, probably we can take one more question. Oh, I do notice there's one in the chat room here.
Okay.
So I think let's take down to the last one, and then we'll adjourn the seminar today.
Oh, okay. Sounds good. Okay. Akash asked, could you please describe the illustration on the top right in slide 38? Yeah, you're talking about this one. Yeah, that's the one I skipped actually. So thank you for asking, so that I can cover those skipped materials. So it's the lattice type structure design optimizations, because the lattice type structure has a very repeated components. So what you can do with the reduced model is you actually build a reduced model for each component, right? So for example, this particular components we generate and then build a reduced model for each one of them. And what we do in the component-wise reduced model is that you assemble those component reduced model into very interesting, the computational, the domains with a lattice type structure. For this particular problem, we have formed a L bracket shapes, and then applied, some forcing the pressure comes pressure force here, and then with a fixed boundary condition on there. And using this component-wise reduced model, if you solve the topology optimization with it, then it becomes really fast. Like thousands of the speed up is achieved, and because the physics is incorporated with this high dimensional parameter space, we can still get the relative error of less than 1% pretty easily. And once you get these results, the optimal results, you can get high dimensional the information you can extract from the component-wise reduced model codes, it can reconstruct the high fidelity dimensional data as well. And this is an example of the stress field we can recover using this component-wise reduced model at the optimal design of the lattice type structure. Very, as you can imagine at the corner, you get the stress concentrations. This kind of recovery, reconstruction, you cannot get that using like, traditional homogenization methods or the truss type of the methods. So we are really excited about that. And yeah, Akash, thank you so much for asking that question so that I can cover everything I prepared.
Thank you so much.
Sorry, just a follow-up. So it looks like you can start with an over-parameterized model, and later, based on your simulation, you could get rid of regions that you don't necessarily need based on what is that?
Yeah, what is nice thing about it, if you just look at the global problem, then the number of parameters is scales with the number of components, right?
Mm-hmm.
But if you build the component reduced model for each component, then the number of parameter is very small, like 1 or 2. So the construction of the reduced model in component-wise is really becomes advantageous in terms of the number of the size of the parameters and also the dimensionality.
Okay.
And yeah, I mean, you can assemble them and yeah, very
looks like
way.
This was inspired by the Livermore logo.
Livermore logo? Oh, I haven't thought about that, but yeah, maybe I should use that.
The solution looks like that.
Yeah. Well, thank you for pointing out. Yes.
Okay.
Yeah. Thank you so much. Thank you. So Youngsoo, we are looking forward to working with your team on LibROM, and thanks a lot for giving the talk on your work, and it's
looking forward to it. Yeah.
Okay. Thank you. I think that's concluded the seminar today. Thank you all for joining. I'll see you next time.
All right. Thank you.
Bye-bye.
Bye, everyone.
Thanks so much.
Thank you.